series that we're doing. It's basically what was an all-day workshop, and we put it into sessions, 1-hour sessions broken out. So what we're talking about today is the emerging codes and code changes that we are seeing. And there's a lot more talk on commercial building codes, especially HVAC and ventilation is a big part of that that's happening across North America. I'm going to talk about some of that. And we're also going to talk about the actual design. Basically, ASHRAE is what it really boils down to, standards for ventilation rates. And I am going to introduce today some slides that are dealing with today's world. COVID-19 and ventilation is top of mind again and again. I'm going to show you a couple of slides that have some stuff I picked off the internet and stories. There's a New York Times article by someone from Harvard School of Public Health, and ventilation is really a huge part of the conversation. So I want to relate that today to where these codes and standards are and where the standards for amount of ventilation we use, and tie that all in and to basically today's world and how to plan for now and for the future as far as ventilation goes. So what we're going to start with is the emerging codes, and there are some changes that are happening to building codes in the commercial world. Make sure I'm on my clicker here. So first, I'm going to just talk about Canada, and what they've done for the most part across Canada is commercial code. These charts look very complicated, but basically this is continuously operating ventilation systems. And what it is the requirement, the R in the bottom corner there of that chart, is requiring heat recovery, energy recovery systems for outside air. And as you can see, it's only required in that zone 8 and zone 7 at certain percentage of outside air in your airflows. So what they're saying is that if you have higher volumes of air and a higher percentage of that volume in those colder climates, that they require heat recovery, energy recovery, ventilation. This is for non-continuously operating ventilation. So what this means is less than 8,000 hours per year is considered non-continuous. So if you're on a schedule or doing part-time ventilation, then you can fall into that. If you go to continuously operating at over 8,000 hours per year, as you can see here, it's required almost universally, all zones but zone 4. And zone 4, it's based on your airflow and percentage of outside air. But the trend and the move is very strongly in all of Canadian code to go to heat recovery, energy recovery, ventilation in all systems. And so this is something that's, I know that in British Columbia, they require, this is commercial, they require heat recovery ventilation or energy recovery ventilation for residential and commercial applications universally. It's part of code in the whole province of British Columbia. It started in the city of Vancouver. It's now spread to the entire province. So all buildings are requiring heat recovery, energy recovery, ventilation systems by code. Then you have a Washington state, which is really leading in North America, in the United States. Their commercial code was originally started on July 1st of 2018 is virtually requiring dedicated outdoor air systems for all commercial buildings with a few exceptions. You'll see some exempted on that little chart there. Again, you'll be able to get these slides and look at all the little minutia here, but bottom line is what you're looking at is inclusions are lecture halls, community halls, all occupancies, not specifically exempted. So these are the different occupancy classes. What it really entails is most commercial buildings with few exceptions. There was an exception for multifamily up until July 1st of 2020. And as of a couple of weeks ago, multifamily buildings applying for permits for building now in Washington State will also require dedicated outdoor air systems. So it is a decoupled ventilation system, and heating and cooling cannot be all included in one package as in rooftop units that are doing heating, cooling, and ventilation. And so that's the code in Washington State. And then this little section here, energy recovery ventilation with DOAS, it shall include that with few exceptions. So they're requiring energy recovery, heat recovery ventilation in Washington State commercial buildings for most cases. And they have some minimum efficiencies for doing that. All right, so Washington State's moving very quickly into a dedicated outdoor air system. It's a pretty important thing. We're going to talk about that in terms of today's world. And they're a little bit ahead of the curve on some things. And they have an efficiency, in effect, reach code. Their Washington State has credits available for reaching an energy efficiency benchmark. And so additional energy efficiency credit requirements you have to meet by gathering 6 points total from different metrics that you can use from an efficiency perspective. So this is a chart that shows you all of those different metrics. So more efficient HVAC, reduced lighting power, reduced lighting, enhanced lighting controls, on-site renewables, dedicated outdoor air system. High performance dedicated outdoor air system gets you on all of these different types of buildings, commercial building occupancies that we talked about earlier, gets you 4 points out of 6. So it's a huge thing out in Washington State to meet their efficiency requirement using a dedicated outdoor air system with very high efficiency, and that's specified here. That's an 80% heat recovery efficiency and 0.5 watts per CFM in operating fan power. So that is, in a nutshell, that gets you pretty close to where you'd be for a passive house ventilation, heat recovery ventilation system. So that's a big deal in the state of Washington, and that's where codes are going. I know that they're looking at this in Oregon, they're looking at these things in California, and probably we'll start to see some following suit in other states that are adopting this, either similar or same code requirements for buildings. I believe that what's happening now with COVID-19 and this pandemic we're dealing with is going to hasten people to have those conversations more readily, more quickly. And we'll probably see adoption of that much more quickly. All right, so that's the biggest moves in the code requirements across the country. And there are REACH codes that are incorporating ventilation as part of a total REACH code. And I didn't get into all the minutiae and details of those, but you'll see where there are efficiency REACH codes that often are requiring heat recovery ventilation and dedicated outdoor air systems, but it's not actual code yet, but they're using it as REACH codes or other similar requirements in some states. All right. So what I want to talk about from there is that ventilation requirements and what we need to do for ventilation. And by code, there are minimum requirements, and I want to talk beyond code, especially again with what's going on today. So when you look at how much ventilation is needed, the International Mechanical Code is the primary driver. ASHRAE 62.1 is the commercial, it's not a code. ASHRAE is the engineering design guidelines or a standard, but it is not a code. The code is the International Mechanical Code, the National Building Code of Canada. Those are set by the local jurisdictions. They reference in the International Mechanical Code, ASHRAE 62.1 is typically the basis for it. but they may take ASHRAE 62.1 in your local jurisdiction and by state generally. They may adopt ASHRAE 62.1 and the International Mechanical Code entirely, or they may have some exceptions. They may not adopt some of the metrics that are in that code locally. So, you know, this is a thing when I have people ask our organization to help them with design or figuring out their basic ventilation requirements, my standard response is, I will do it to basically ASHRAE 62.1, but you need to check with your local code official to make sure that that is the IMC or ASHRAE 62.1, if that's referenced, make sure that that is what their jurisdiction is requiring. And I have seen it where we did a design and then the local code official said, no, we do this differently. You've got to do this, or you got to do that. So that has to do with the design flows, which are what we're primarily talking about today. But that also is things like fire dampers and other metrics of the International Mechanical Code for requiring duct sizing and again, fire dampers, smoke dampers, that type of thing. Always check with your local jurisdiction. So all of these standards will have requirements for ventilation. I'm just going to move this so I can see my slides better. So the National Building Code of Canada, and as I mentioned, it references ASHRAE 62.1 for flow rates. So basically you open the National Building Code of Canada and it says, okay, for ventilation, refer to 62.1, and almost without exception. (62.1) has tables that you use that will determine what the airflows are and how to calculate those airflows for all of these different, what they call breathing zones and exhaust areas or exhaust zones. So these two tables, one for supply, one for exhaust, are what is referenced and used to determine what your proper ventilation rates are in all these different spaces. And it's pretty extensive. So what you've got typically in a commercial application with ASHRAE 62.1 is on this table, you'll have a description of the room. So in this case, we've got a correctional facilities are first on the list. Isn't that fun? So we've got day room in a jail, basically, and it's the CFM per person, 5. That's liters per second per person. That's done. And then it's got CFM per square foot. So you're going to add those up. So you have the CFM per person that's designed into that space, and then 0.06 times the square footage, and you add those two together, and that gives you your total ventilation rate. Now, there is a default occupant number here. So a typical day room in a correctional facility showing 30 people. It may be that you know that there are only going to be 10 people in that space, or that there are going to be more. So as you're designing this, if you have knowledge of what the actual occupancy is planned for, then you'd want to put that in, and then that will determine your proper ventilation rate for that space. The other thing that's on here over on the right is the air class. And this is very important. When you're designing a ventilation system, you're generally putting air into a space and you're taking air out of spaces. And you want to make sure that the direction of that airflow is going from a low number to a high number. So what you can see here is a classroom is a 1. So that's the highest, cleanest air in the space. And a daycare sick room is a 3. So what you want to do is have the air go from the classroom to the sick room and then be exhausted, not the reverse. You don't want to put a supply into a sick room and have it flow into a classroom. That's going to be exactly what everybody's talking about these days. So you want to have from a low number, high air quality to a higher number, lower air quality based on that chart. And so this is how it's determined. Other things that are a factor, we're going to get into this more in a later session, in another one of these modules, but how that air is delivered is also an important thing. This is called the distribution effectiveness. This is where, when we talk about passive house ventilation and very high efficiency, this can play a big part if you're doing a dedicated outdoor air system. So what you're looking at here is this multiplier is, the higher that number, the better the efficiency of delivering that air and providing ventilation. Remember, what ventilation is dilution of pollution. So if you're going to dilute that space, you want the air to mix very readily and then move through the space and then be exhausted. If it doesn't mix, if it creates clouds, stratification, and that's where you see, okay, let's look at this one. It's 0.8 is not a good way to provide ventilation. Ceiling supply of warm air, 15 degrees Fahrenheit or more above the space temperature, and a ceiling return. What that means is you're going to have that air come into that space in the ceiling. It's going to, if it's warmer than the room, then it's going to stay stratified. It's not going to mix with the air that's down low, and it's not going to dilute the CO2 and other contaminants that are in the air. So you want it to come in and mix readily. And so you look up here, ceiling supply of cool air is a 1. So that's just call it a standard good way to mix air in. Cool air coming in the ceiling is going to settle a little bit. It's going to warm up, and then it'll be exhausted. The best they show here, this 1.2, means you can use theoretically less ventilation air, floor supply of cool air, and a ceiling return. So your air comes in low, and then as it warms up by people and other things in the room, computers and all, it warms up and it rises, and then it's exhausted out. So it's coming in low, leaving high, and diluting as it goes. And it's a very effective way to eliminate CO2 and other things in the room. What's really important is when you look at very high efficiency heat recovery ventilation, that means that you're bringing air into the room from your ventilation system very close to the same temperature that's in the room. So that does mean that your direct ventilation is going to dilute, it's going to disperse into the room very readily. And when I was in my days with Zender, that we had done some theatrical smoke tests where introducing air in just a small vent in a corner of a room, if that air was within 5 degrees Fahrenheit of the room temperature, that smoke would tend to diffuse into the room. The whole room would be smoked up almost universally within a matter of minutes. If that air was warmer or cooler than the air in the room, it would tend to warmer, it would create a cloud and not mix as readily. Or if it was cooler, it would be on the floor and it would not mix as readily. It didn't diffuse very readily into the room as well. And we weren't diluting pollutants in the room as well as a result of that. So that's a really important factor to consider. All right. And then you've got, I talked about the other chart here, table 6.5 is for bathrooms and all the things exhaust. So art classrooms, exhaust rate is 0.7 CFM per square foot. And it's also got air classes shown there. So you've got toilets private, it's 25 CFM per unit, and toilets public, 50 CFM per stall or per fixture. And those would end up balancing out. When we talk about passive house, for the most part, passive house is going to be pretty close. These are just some examples of small disparities between passive house and ASHRAE 62.1. So you're looking at the CFM rate for schools, 9 to 12 CFM, and CO2 limited to 1,500 parts per million. An office is 18 CFM per person. That's higher than what you would typically find with ASHRAE 62.1. Gymnasium at 36 CFM per person is higher. So that's where meeting the passive house standard, you're going to exceed the code, typically ASHRAE 62.1. You don't really have to worry about it, but it's just something to be aware of. Ideally, you have to follow 62.1 or the local code, so you would look at that, compare, and go with the higher ventilation rate of the two if there are any disparities. If you look at just residential, and I just want to give you an idea of this, this is a basic formula that we use just to get where passive house on supply ventilation is 0.3 air changes per hour as a minimum. So if you had a 2,400 square foot, that's your treated floor space. 2,400 using 8-foot ceiling was our standard. You've got 19,000 cubic feet. That 19,200 cubic feet, we're looking at CFM cubic feet per minute. So you divide by 60 to come up with 320 CFM. Our air changes is per hour, okay? So in a minute, we've got to do 1/60th of that. That's 320, and then 0.3 air changes per hour is 96 CFM. It's a very simple formula to give you a guideline on what your supply should be in that dwelling. So this is a really simple formula that we've used, I've used thousands of times, literally, all right? And that'll give you a guideline to work with on supply. You would then do your returns. You'd figure out what your bathrooms at 24 CFM per bathroom and your kitchen, and you add up all your exhausts and you determine which one of those is greater. And then that's your design ventilation rate for that dwelling. And wherever you can, having demand control, if you can do that, is a good idea. And you also have to meet ASHRAE generally for local codes. What we found is typically passive house ventilation rates for residential exceeds the code required. ASHRAE 62.2 is the residential ventilation code. And then there are some variations. You're going to have some of these standards are going to have a variation that is a little bit different than the regular code. So LEED, for example, will give you, LEED and the well building standard will both give you a 30%, or excuse me, extra points for a 30% higher airflow rate than what is ASHRAE 62.1 requires. So by doing more ventilation, they're giving you extra points. One factor there, and I don't necessarily agree with this, and one of the way I put it is better ventilation, not more ventilation. Simply doing more ventilation means you're using more energy. Even if you're using very high efficiency heat recovery to provide that ventilation, you're still going to have an energy penalty for the fans operating, and for, you know, the whole system design has to be designed to provide 30% more airflow. That's going to add both costs on the front side and operating costs to provide it. So I don't necessarily agree that just by adding 30% is a good answer. Demand control and other options that you can use to optimize and make it very effective can be just as important as just adding extra air. So that's just something to kind of keep in mind. And we find that, you know, if you're tracking CO2 levels and using demand control in a commercial application, you're able to manage it very effectively that way, and you aren't unnecessarily over-ventilating. But there are points for that, and you have to design that in. And from the design standpoint, at the beginning, determine if you're going to allow for 30% additional airflows. That said, let's talk about what they're talking, what the conversation is with COVID and It's not hard to find this stuff. I'm just because of the space I work in, I get these emails all the time with all of these different articles that are coming out. And you're seeing big things about how do we go back to work, how do we go back to school, all of that. And the transmission of infections, in this case, COVID-19, is the real topic of discussion. And almost universally, they're talking about now about airborne transmission, which means that the virus is in the air. And what they're talking about first and foremost is more ventilation. Now, one of the factors is that ventilation in a lot of buildings, you read a little bit of the details, is poor to begin with. So you're going from zero to better. You know, opening a window is better than what they have in some of these older buildings. But the key is they're talking about doing more ventilation. And this is almost universal. This was an article by Joseph Allen, who's at the Harvard T.H. Chan School of Public Health. He was involved with the cognitive function study at the Center of Excellence in Syracuse a number of years back that found that cognitive function improved with better ventilation and lower CO2 levels. So, you know, he wrote an article in the New York Times recently, and I just picked a few things that are, you know, right out of it. Proper ventilation, filtration, and humidity are what he's talking about. This is really interesting, okay? This is 46 years ago. A young girl with measles went to school in upstate New York and spread it throughout the classes, and ventilation system, they determined, had spread measles throughout the school. So basically what they have on top of that school is these rooftop units that recirculate to provide ventilation theoretically and heating and cooling. And because of that, it spread that all through the school. That was 46 years ago. And today, I am sorry to say, we are still putting the same equipment on top of the roof. So looking at it today, this was a cruise ship that had a major outbreak. Well, guess what the ventilation system is on the cruise ship? It's a recirculating system that's moving air throughout that cruise ship. And as a result of that, the theory is, they're still studying it, but the theory is, you know, at 3,000 people and 700 of them got infected. And they were locked down pretty early in that cruise. So I think that you're talking about something that's being spread about the ship. It's probably something to do with ventilation recirculating. So this is what, in that article, Dr. Allen talked about more ventilation, which is universal, and bringing in more outside air and diluting the space, number one. And he references a study here that was just last year that shows that flu transmission was reduced dramatically by providing more ventilation. And then high filtration. Don't recirculate, provide more ventilation, and use MERV 13 filters. Guess what Passive House requires for Passive House certified ventilation systems? A MERV 13 filter. So it's standard and ready to go. Passive houses are healthy buildings and meet all the top issues that everybody is dealing with. It's a dedicated outdoor air system with a tight system. The ventilation system does not have cross-flow contamination, and it uses a MERV 13 filter. Good to go. All right. So that is, you know, where everything is at. And so one of the things that I've seen on a takeaway of all this is they're talking about going back to school, going back to the office, and I'm seeing all sorts of webinars that I've been sitting on by consultants and industry people and ASHRAE, and they're talking about these three metrics: more ventilation, no recirculation, higher filtration. they're talking about retrofitting existing equipment to do that. I'm talking about taking a packaged rooftop unit that's bringing in 20% outside air right now and turning it into a dedicated outdoor air system. Well, that may work when the temperature is right. You can open it up and just call it economizing. But when it gets cold, which is absolutely possible that we'll be still dealing with this in the wintertime next year, and opening that up, you're not going to have enough heat capacity to heat up 100% outside air when it's only designed to do 20% of outside air now. You're also going to use bigger fans, whether the fans can even handle it. They're talking about adding MERV 13 filters. And if it's designed for a MERV 6 or a MERV 8 filter, you stick a MERV 13 filter onto that unit and the fans aren't going to operate. It doesn't have the capacity to even deliver that air. You're going to burn out the fans, have other issues. So, you know, it's kind of like trying to make chicken, butt out of chicken, what. And I see that and it's like, geez, you know, this is really a challenge. It's not going to be a long-term fix at all. You might be able to get away with short-term doing something like that. The other conversation we have when I've sat in on these workshops and presentations is that it's, well, you know, we can do this, but it's going to be a huge energy penalty and it's going to cost a lot to do that. And it's right, because when you do put on a MERV 13 filter where you used to have a 6, your fans are going to use 2 or 3 times as much power. And you open it up and you're bringing in all that outside air, you're going to have to cool it or heat it and dehumidify that air 100%, and it's going to have a huge penalty. If you had been using a dedicated outdoor air system with very high efficiency heat recovery, all that goes away. And in another later session, we'll bring it back again. I've been talking a lot about this over the last number of years, retrofitting buildings to put in very high efficiency heat recovery ventilation to do a dedicated outdoor air system, and then putting in heat pumps, and you save an average in offices, we're saving an average of about 70% of the energy to do that retrofit. And now we've met our ventilation and filter and you know, more outside air that we're after, and we can pay for that by doing huge energy savings. So that is a solution, but you have to really look at this in terms of ventilation in commercial buildings, trying to in effect change existing systems the way they operate as opposed to changing the actual systems is going to be a real big challenge. So that's something to be aware of. All right. So with that, what I'd like to do now is take you on into our design tool. And I'm going to show you how we lay out a building and determine how we're going to determine the ventilation rates and so forth, and some design tool little tricks we use to help lay it out. So what I'm going to do is punch out of here. And should be right there. Everybody should see that. And remove this. Try and maximize that. So this is our design tool. So I've put in just some basic design conditions. We're not so much worried about this right now. This is what we use to determine our ventilation efficiency. I've got a 3000 CFM unit running a 2400 CFM. I want to touch on that now as well. For many years, it's probably 10 to 12 years now I've been doing this. When we talk to people about installing ventilation systems, we don't like to just install a system that's operating to meet your minimum requirements for ventilation at capacity. In other words, a 3000 CFM unit, I don't want to put that on the roof if you need 3000 CFM or even 2900 CFM. And there are a couple reasons for that. One is it's at its least efficient operating at capacity, both for heat recovery rate. Obviously, if you're moving air more quickly in both directions through that heat exchanger, maximum volume in both directions, you're going to have a lower level of recovery. And your static pressure, which means your fans, are going to be using higher amounts of electricity to move that air. The biggest thing is that in a time like we have now, where they're saying, increase your ventilation, do more ventilation. It's nice to have some capacity that you can run for a period of time in something like a, outbreak of a virus or flu, or even in flu season. It would be nice to be able to just crank up your ventilation a little bit, do more ventilation for that period of time when you need it. So, it's one of those things that we've been talking about for many years. Now, in a time like this, is when it comes back and it's like, yeah, it'd be nice to have that capacity. We shouldn't have designed it to be at capacity that we don't have any room to add a little more ventilation. So that's one more reason to design that way. So that's one other thing I wanted to mention. So we have in our design software a flow calculator, basically, that's got the ASHRAE 62.1 numbers in it. And I've done a little bit ahead, laid this out, and I want to just have it take you through this, and I'll show you how we would look at a larger facility that's got a lot of spaces and how we would want to approach this in doing their ventilation design. So I did just a small school, call it, just for demonstration purposes. So I took 6 classrooms. I've got a lecture hall, a cafeteria. I've got the offices. I've got a reception in the office area, and I've got a gym. And so I've got default numbers that go in when I put in the square footage for all those spaces. This is the code assumed number occupancy. And then this is the airflows based on that formula of the square footage times its multiplier and the default occupancy, say 5 CFM per person in a classroom, for example. And so I look at this and I say, okay, I'm going to have in this classroom, I'm actually expecting to have 24 students sit in that classroom. It recalculates, determines what it goes from 228 to 298, as you can see there. And I do the same, and you go down through, and this would be the most you would be planning for. And I'm going to put 30 students into that 540-foot classroom. And so you just go down through and you put these numbers in. And that's pretty good for the lecture hall. 300, that's pretty high. Food and beverage, 224 in the cafeteria. Offices, pretty much that's typical, designed for one person. I could put in 2 just to, in the reception area, I should put in 6. And then the gym is on a default number based on the volume, or excuse me, the square footage. So I can go through very easily, figure out what my ventilation rates are going to be in all of those spaces. Then we have a zone builder that allows me to go into each zone and break it out into zones. And this can be really helpful to allow you to figure out, okay, what am I going to use for equipment and the equipment capacities to do this school? All right. So in this case, I've got a VS 500. I'm going to put in all the classrooms, call that 1. I'm going to use 500s with decentralized ventilation for the classrooms. They all are under 500. And those are those individual zones. And you'll see it calculates now. This is my remaining in this zone, call it, that's left, 7,400 CFM. I'm gonna, in the lecture hall, because that's gonna be demand control in a big space like that, absolutely the best way to go. Put it on CO2 and use it. If you've only got, the lecture hall, if we go back here, is designed for 300 people, and you've only got 20 people in there, you obviously don't want to be running at that full 2,200 or 20, higher than 2,200. So, yeah, lecture hall's there. It's got its own zone. Cafeteria, I do the same. And then the office, if you look at all those offices, you add those up and you're looking at 20, 40, 68, 78, 86, 120. You're looking at only about 150. So you could do a small unit and use the same one. So when I put in BS 250-1, you'll see as that becomes a zone with all of those together. So there's that whole zone at 86 CFM. You can do the reception too. And I've got that whole zone done together. It's 125 CFM in that zone. And then I've got the gym. One more unit. And I've broken it all out into zones, and I can determine what I need for equipment and tie it all together and then design the ductwork accordingly. So this allows you to take a very complex building, an office building with all different types of spaces. You may have retail on the ground floor. You may have apartments up above. You could literally take the whole building and put it into this and break it out into zones, determine what all your ventilation rates are, and kind of cut your time down on determining and designing the ventilation for the spaces. So it's just a tool that really is helpful to look at these multifaceted buildings and get your ventilation worked out. All right. And that's it. So you've got these three are on 3000s. These are all individual ventilation units in each classroom using demand control. And then all the small offices are on a single unit. That's one zone. And there you go. So this is a really easy tool to help you go through this and, like I say, lay out these more complex buildings. We use this pretty regularly to get us a guideline on how to approach this. All right. So that can be really helpful. This tool is it's a Google document that we have developed, and we can give anybody who wants access to that. We can give you basically an access, and you get your own, in effect, Google files and so forth, and can access the tool, and all of your calculations that you've done, all of your different projects be stored right in your own files. So it's pretty helpful to have. So you can look at the efficiencies, you can look at your remaining loads for your ventilation. This is outside air load, raw outside air load. This is your HRV remaining load, your ERV remaining load at design conditions. For on the top is summer, the bottom is winter. And you can see what your remaining loads are for your heating cooling system. All right. So that's, again, available, and you can send me an email and I would connect you with Jonah Peskin in our office, who manages that files basically, where everybody gets access to it and can utilize that tool. It's a really helpful tool. All right. And with that, it pretty much wraps up what I really wanted to talk about today. That gives us a lot of really the foundation that we're going to be talking about in subsequent sessions that are going to be scheduled going out. The next one is going to be about what's in the box. It's really, I think, my favorite. We're going to talk about HRVs and ERVs and deep down what's inside and how they work and what makes them efficient, and what are the tricks to getting very high efficiency and getting Passive House certified. And I do want to talk about, during that, I talk about Passive House certified versus AHRI, HVI, North American, tested, the different testing standards and how they differ, and really give you some good insights into how those things really do work. So with that, I'm going to take questions.
But so there are a couple of questions regarding ventilation, mechanical ventilation, and also regarding natural ventilation at the same time. So if someone opens the window, how much of that air through the ERV is filtered or not filtered?
Well, if they open, everything that goes through the ERV or HRV is going to be filtered. But if you do it, obviously, if you open a window, it's not a system where you're moving air efficiently and effectively like you design it. So that's just going to be a factor, but you're still going to be providing fresh filtered air into the space. And I once saw, I don't have slides on it and so forth, but I once saw a study that was done in Germany about opening windows, and it's much less effective than people think. The conclusion was, this is from Eberhard Paul, Dr. Paul, and the conclusion was very surprising how ineffective at really ventilating and diluting the space opening windows was. And of course, there's a lot of variables. This is on the windward side or the leeward side of a building, and other factors. Were the windows open on both sides of the building or only one? There's so many variables that it's hard to determine what is really effective. But the bottom line was, they said opening windows is much less effective than a balanced ventilation system that it's moving air through the space, both positively with the fresh air and negatively with the stale air, is going to be a continuous movement of air that's going to be very predictable and consistent, as opposed to windows that are much less so.
So I think, Suzanne, you had a couple of questions. You can unmute yourself and probably ask a question yourself if you like.
Okay, yeah, I did have a couple of questions. I'm trying to remember what they were. Here we are. Yeah, it was just at the beginning, Barry. Thank you very much for this, very helpful. When you were talking about that Passive House requires a higher amount of CFM than ASHRAE or code, I was just curious, if this were just a traditional building, like forget about the insulation and thermal bridging that's been done with Passive House, I'm understanding that the ventilation unit would therefore be much bigger. I mean, you went on to talk about that, but I'm just curious, in the Passive House, I haven't actually done a Passive House yet, how much does the insulation and thermal bridging, how much does that play into the effect that the size of the unit is actually reduced, even though you're putting in a higher CFM? Does that make sense?
Yeah, it really won't have any impact. This is an interesting thing. And there have actually been people out there saying, well, heat recovery, balanced ventilation in an old leaky building isn't effective. And that's just not true at all. It actually is more effective in an old leaky building because you're not depressurizing or pressurizing it which rooftop units that are on an old building, we've done a lot of these retrofits, and you take off a unit that's just opening a damper and dumping fresh air in through the recirculating heating cooling system, you're pressurizing the building, which means in the wintertime, you're pushing warm air out of the cracks. And if it's a leaky building, you're pushing a lot of warm air out of the cracks. Whereas if I'm doing a balanced ventilation system and it's neutral, I'm not pushing warm air out through the cracks, nor am I pulling cold air in through the cracks. And so as a result of that, that means that the ventilation with a balanced ventilation system is very, very effective. And you know, that's been really an interesting thing to hear, that theory that, well, it's not really worthwhile to put an HRV or an ERV into an older building that's not been air sealed and insulated. It's not true at all. And I can show you, there's case studies and you can go see them, or I can send them to you, or, you know, they're all that we did with the Northwest Energy Efficiency Alliance. 2 of the buildings were from the 1930s, and they did a blower door test. One of them was 8 air changes at 50. That's not tight.
It's like an open window.
And we reduced the energy use of the HVAC by 85%. Okay, so, you know, if they go air seal and insulate, we'll probably be over 90. So it really is, you know, a thing where that's not going to play a big part.
Great, thank you.
Okay, and I think Caleb, you have a couple of questions you could.
Yeah. The slide you showed with the EZ coefficient, I think it was from 62.1 early on. I was curious because that most of that seemed to be more conventional air conditioning and ventilation systems where you have a big delta T. And so the first question with ERV, because the temperatures tend to be lower even without adding reheat, does that coefficient really come that much into play? And then what happens since with an ERV between, like in summer versus winter, where you'd be supplying cold or warm air depending on the season, you know, how much does that chart really come into play? It was just sort of a wonky question.
Well, I think because that chart talks about a 15-degree delta T.
Yeah.
And if you're at a highly efficient ventilation, you know, heat recovery or energy recovery, whether it's summer or winter, you know, in the winter you'll be a few degrees cooler, and in the summer a few degrees warmer, but it's only that few degrees. So for the most part, you're going to be on a multiplier of 1 for a standard ventilation system that's providing air at near ambient temperature.
Okay.
So it wouldn't be a big factor. You're right, that ASHRAE chart is really about, you know, VAV systems that are recirculating and doing heating, cooling, and ventilation. And that's where because you're tying the ventilation air into that single airstream, ventilation is not going to be very effective if it's warm air or if it's cold air, especially if it's warm air and it goes to the ceiling.
And then the other question I had was, like, in your example for the classrooms, you chose to do unitized. That was just like an arbitrary decision you made, I'm assuming, because you could potentially, depending on how closely they are together, you could probably do that with a larger unit too, correct?
Yeah. I just wanted to show, you know, a varied amount in zones and so forth for the example. And we are doing a lot of that. And, you know, I'm going to be doing next week, back to school COVID-19 for schools specifically webinar, and talk about how we can retrofit existing schools. And that's one way, is using a small, you know, a decentralized unit in each classroom to provide both supply and return. This is where you've got to, if you were doing 6 classrooms with a single unit on the roof, for example, you'd have to put supply and return into each classroom to avoid moving viruses and germs and so forth between spaces. A lot of the systems are designed where they're blowing air into a classroom, for example, and exhausting out of the hallway, or vice versa. And that's not going to be as optimum. So our solution for schools is to have each classroom have a decentralized system that does both ventilating, supply fresh air, filtered air in, and exhaust air directly out in a single classroom.
Do you know if air movement would make a difference in a classroom, just like speeding up diffusion of what is actually, I mean, it's still a kind of a recirc condition, but at least it's not allowing for air to stratify and concentrate. I'm just,
Absolutely.
I'm dreading going back to work actually in September at like teaching at Pratt with its old buildings and pretty much non-existent ventilation and wondering what they're going to be doing.
Yeah, well, we're going to be talking to them, whether or not, changing thousands of buildings or millions of buildings before people want to go back to work or back to school is going to be a big challenge.
Yeah, I know.
It'll be a one at a time thing, but there are opportunities. We're real excited about it because we've got this solution that also saves tremendous amounts of energy. And so you've got a way to pay for it. Not on day one, but you can, borrow the money and then fix all these schools and fix all these offices. We just did an office in Terrytown that I've used as a case study that just got completed in, I think it was April. It was almost a year process to transition from a rooftop unit driven building to a heat pumps and ERVs building. So it has a dedicated outdoor air system in an office building in Terrytown, New York, that is now a healthy building to go to work in because it's got exhaust out of every office and supply of fresh air that's, MERV 13 filtered fresh air in. So we basically, they had no idea that they'd be facing what they're facing. They were looking at energy savings and we're going to save them about 70% of their energy. We are looking right now, they're going to save $200,000 a year in energy costs. Nothing to scoff at. So, that's where passive house ventilation, call it, leveraged into a retrofit can be an incredible tool to make offices and schools healthy. I'll tell you, there's a passive house gym in New York, in Brooklyn, that I think just got commissioned. It's going to be the healthiest gym in New York.
For sure. So there's a question by Jeff, if you actually make that tool available, or is that tool only one?
Yeah, we can give you access. So I need to have you send an email to barry@ventacity.com. Just say you want to be able to access the Ventacity design tool. And
okay.
then I forward that, I run that to Jonah Peskin, is in our office out in Oregon.
Okay, I would say,
manages it, but you just send me an email and I'll get you access to it. You'll get an email from Jonah with a password and usually I think it's your email, and it'll say, here's your access.
Follow-up email will make Barry's email available for everyone, and then you guys.
Yeah, so just send me an email and I'll set you up with access. We try to do it with one account per firm. So if we have, engineering firms, we'll get an account for their firm, that type of thing. So we don't have thousands, we only have hundreds of people.
Right. And I think, Lindsay, you had a couple of questions, if you want to unmute yourself.
Yes, hi, thank you so much, Barry. It's fantastic. Quick code question. In New York, a residential use building that's 4 stories or more is commercial. So if you're designing the HVAC, do you therefore use the 62.1 and the international code that you were talking about?
I believe so. I'd have to check on that because one of the things is ASHRAE 62.2 for low rise and residential. And up until recently, ASHRAE 62.1 for multifamily was different than ASHRAE 62.2 for residential. The latest version of ASHRAE 62.1 for multifamily residential references you back to 62.2. So you've got to meet ASHRAE 62.2 residential code. But whether or not New York, I don't know if New York has adopted that yet. Do you know that?
Andres, do you know?
Andreas?
Okay.
So
Also,
we'd have to check locally, but it will be eventually when they, it always takes them time. So the latest version of ASHRAE 62.1 in effect adopted residential ASHRAE 62.2. So that means ventilation for kitchens and bathrooms and so forth are all, you used to be able to have an operable window and that meant your ventilation rate for multifamily in 62.1. That is not going to be that way anymore. But when they adopt that new ASHRAE, every 3 years, ASHRAE redoes the standard.
okay, and then this is maybe a question that we passive house people could comment on, but if you'd mentioned, if you have a ventilation system that's balanced and you have a leaky building, that it would still help, and kind of goes against what the passive house community purely is thinking about in terms of maybe protecting a building. So from a ventilation standpoint, that might work, but it might not work from the point of view of creating problems in terms of moisture buildup inside the building walls. I don't know, Andreas, you might be able to comment on that.
Or I didn't listen because I was.
Oh, I'm sorry. Oh, okay.
I can comment on that.
Yeah.
And then Andreas can correct me probably because I'm not an envelope specialist, but all my focus has been on the ventilation side. But once again, think of it, the moisture issues in walls are when moisture is leaving the building through cracks and then reaches condensation, basically reaches dew point in the wall, and then you've got moisture in the wall, and that's a problem. And then in the wintertime, that is definitely a problem. As it cools on its way out, it may find its way to become moisture, become water from water vapor somewhere inside the assembly. But if you're doing continuous ventilation, that's going to help a lot and be a really big factor in not having higher humidity inside the envelope, inside the building in the wintertime. The other thing is you're not going to be pushing warm, humid air out or drawing cold air in that's going to potentially intersect with and cool off inside of your wall, for example. So if you're at neutral, it's still going to be helpful, I think, even in a leaky building. So
I think that's really important because
that said, you're still going to have moisture movement in an uninsulated or a poorly sealed assembly.
I mean, that can be very important because, for instance, people who own townhouses, for example, who they may have been renovated within the past 10 or 15 years, they are asking if they can have this balanced ventilation system and also if they can change up their HVAC systems. But to strip the entire building down to gut it and air seal it is not practical given the building has only been renovated, within the past 20 years.
Yeah.
So what you're saying is kind of radical in a good way for those people.
Well, I can tell you, putting a balanced ventilation system in is where they have now probably a outside air system blowing air into a hallway and then bath fans pulling air out. And that's your ventilation system, which is not a ventilation system.
Yeah.
And replacing it with, and this is challenging in these multifamilies, it's one of the biggest challenges in the building world is getting ductwork to supply and return out of an apartment, for example, and do it. If you've got a plenum down a hallway, then it's very doable. But a lot of times I've been on projects. We had a Marriott hotel in Rhode Island, in Providence, Rhode Island, that we looked at extensively, and we had proposed doing it, but they ended up, from a cost perspective, it was extremely prohibitive to drill down, and basically we were going to take the vertical ducts that came from all of the bathrooms, bundle them on the roof to an HRV, and then run another drill, basically another duct down next to that, and then supply into each one of those apartments. So you'd be drawing out of the bathroom and supplying it into the hotel room, basically. And they were putting a heat pump system in, and would have been a transformative to that hotel. They didn't do the ventilation, they did the heat pumps. And they have electric resistance makeup air blowing into the hallways and exhaust out of the bathrooms, and that's the ventilation. And they have mold behind the wallpaper in the rooms.
I think it's important to keep in mind that, once you start insulating your walls and your building envelope, you have to have an airtightness layer in order to protect your wall, right? I mean, you could do, like Barry does sometimes, do balanced ventilation, fresh air ventilation with a not so airtight building. I mean, you certainly have the benefits of controlled ventilation and some ERV, heat recovery. But once you start to insulate your building, of course, the airtight layer is really to protect your walls from, that moist air in the wintertime going through your wall.